Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, we will continue our lecture 12 on the introduction to fatigue. So, this is the outline of this two-day lecture. The first one is the fatigue loading. Second, mean stress effects. Third, fatigue test. And then S&N curve. And the last one is the endurance limit factors. So, for the introduction, the discussion in the preceding lectures described the fracture behavior of components subjected to a monotonically increasing load. However, most equipment and structural components are subjected to repeated fluctuating loads whose magnitude is well below the fracture load under monotonic loading. Examples of equipment and structures subjected to fatigue loading include pumps, vehicles, earth-moving equipment, drilling rigs, aircraft, bridges, ships, and offshore equipment or offshore structures. So, fatigue. If the nominal load is repeatedly applied and then removed to and from a metal part, known as a cyclic load, the part would break after a certain number of load-unload cycles. Means that there is a process of mechanism between load and unload and it keeps repeating. So this behavior is known as fatigue. Fatigue refers to the initiation and gradual propagation of cracks under cyclic loading. Fatigue is the cause of about 80% of the breakage that occurs in machinery. So, if you see this figure, this graph, the crack length versus elapsed cycles n, and then of course you start the crack with the crack nucleation, and then it grows until it reached the fracture point. Okay, there is two types of most common known fatigue loading. The first one we see that as constant amplitude loading, stress loading. Why we say this? This type of loading usually occurs in machinery parts such as shafts and rods during periods of steady state rotation. We say that as steady state. Right? You can see here the constant amplitude means that the amplitude will be maintained the same. If you see it start with a certain number of stress, and then it keep increase, and then it reach the maximum stress here. Now it's going unload until it reach a certain number as well, and then it's go back to the same amplitude as before, and then the process is keep repeating. Okay, let's take a look at the random stress loading. This type of loading is experienced by many structures, including offshore drilling rigs, because due to the wave of the ocean, and then ships, the same, and then aircraft due to some kind of interaction between the turbulence, the gas load, and so on, the same with the bridges, and then earth moving equipments. So if you see the applied stress is not the same or not constant, that's why we didn't say that as constant amplitude, but it is random because it can be at this point and then it can reach at this point, and it's not consistent along the way of time. Okay, please remember that fatigue is a time dependent failure. You can see even when we plot the stress time graph, it start with the certain number of time until it reach a certain number of time, and that's how we see the behavior of the fatigue. Okay, for the constant amplitude fatigue loading, there are different type of fatigue loading, which is reflected to the constant amplitude. The first one, varying load superimposed on a constant load. Second, 0 to max to 0. And then the last one is fully reversing load. If you see at this figure, the varying load superimposed on a constant load, you can see the plot is not reaching any value of zero stress. It must be started from a certain value and then it keep reaching at the peak of that plot or the graph, and it's going down a certain number as well, somewhere here, and then it keep going back until it reach the same value as before, and then the process is keep on repeating. So this is the stress plot versus the time. If you see the 0 to max to 0 graph, the same, the plot between the stress versus time, and then it start with a certain value of stress, it reach the highest peak of the graph or the plot, and then it keep going down until it reach the value of zero stress. That's why we say 0 to max to 0. And then the process is the load is keep repeating. Okay, this is the definition of how we calculate for each parameter. For example, the stress ratio, we take that as the R equal to sigma mean divided by sigma max, where you can get the sigma max from, let's say we take this case from the zero value of the stress up to the highest peak of the plot. So divide by, this is the sigma max, while sigma mean is starting from the zero stress up to the lowest peak of the plot. Okay, so what is stress range? Stress range is sigma R, where we can get that as sigma max minus sigma mean. So it denote that as sigma R, stress range. And then the alternating stress, sigma A, here, and also here, because sigma max, sigma A is actually sigma max minus sigma mean divided by 2. That's why we can get this value, and then you can get, you can divide the value as 2. Okay, the mean stress, the average stress, or we refer to the mean stress as sigma m equal to sigma max plus sigma mean divided by 2. So note that R equal to minus 1 for a completely reverse stress state with 0 mean stress. Okay, now take a look at this plot where it is difference compared to the other one, which is this is the constant amplitude fatigue loading, while this is variable amplitude fatigue loading. These are generally very complex, but for analysis purposes can be simplified and described by analytic functions and represented by various parameters. For example, if you see this plot, this is quite constant until it reaches a certain time and the peak has increased. But this is only one. That's why we say that as single high cycle superimposed loading. If you see the same trend, but we have a multiple high cycle, so we say that this is as the multiple high cycle superimposed loading, where the high cycle they have the same amplitude. Okay, the same amplitude for the highest cycle, and then it keep the same as a constant value as before. But if you see, this is the most randomly case where the variable multiple high superimposed loading. all of the amplitude most likely not the same or not constant, and it is some kind of having a variation in terms of the amplitude. Okay, the determination of fatigue strength of a material, the fatigue behavior of a specific material, heat treated to a specific strength level, is determined by a series of laboratory tests on a large number of apparently identical samples of that specific material. For example, if you take an aluminium material, you just need to have several types of identical samples. From that, you can see what is the behavior of the fatigue strength of that material. So, experiments are performed on a rotating bending machine. So, this is the fatigue test specimen. A large number of tests. Okay, this is about the fatigue test. A large number of tests is run at each stress level of interest. Means that at what level of interest means at what value of the stress that you want to test. And the results are statistically measured to determine the expected number of cycles to failure at that stress level. The cyclic stress level of the first set of tests is some large percentage of the ultimate tensile stress, or we refer that as SUT or sigma UT, which produce failure in a relatively small number of cycles. Subsequent tests means repeated tests are run at lower cyclic stress values until a level is found at which the samples will survive 10 million cycles without failure. The cyclic stress level that the material can sustain for 10 million cycles is called the endurance limit. So this is the denotation or definition. We can represent that as SE or sigma E. So all of the result will be plotted in SN curve. So this is most likely represented. We represent the failure in terms of fatigue test curve. Okay, this is the SN curve where you can see the fatigue stress SF versus the number of stress cycles N. At the value, if you see, we get the first value as SUT, and then the trend is keep reducing until certain value of cycles. So here we see that as low cycle. Beyond that, beyond more than 10 power of 3, and then until it has an infinite number, we say that as high cycle. If you see here, the trend, we have a linear trend here, and then the slope of this graph up to here has been changed until it reached a value where the fatigue strength is constant. So here we set that as SE, the endurance. We set that as endurance limit, SE. Right, the fatigue strength. The fatigue strength, sigma F, is the stress level that a material can endure for n cycles. Endurance limit, sigma E, is the stress level at which the material can withstand an infinite number of cycles. So this is the plot in terms of log. Okay, fatigue life evolution, SN curve, alternating stress amplitude, SA, versus number of cycles, NF, to failure. So, this is the plot of SA. Versus the NF, the cycles of failure, where we know where the result as we constant is sigma E or SE, the endurance limit. Some materials, such as steel, show an endurance limits stress below the fatigue life is essentially infinite. Other materials may not show such behavior, but an effective endurance limit may be specified at some large number of cycles. So, endurance limit, or we always say the SEL factors, because of sigma E values are statistical in nature and determined on optimized laboratory samples, good design practice requires that one tries to determine what the actual sigma E will be for each specific application. In order to design for satisfactory fatigue life, good practice requires that the laboratory endurance limit value be reduced by several adjustment factors. These reductions are necessary to account for the first one, the differences between the application and the testing environments, and the known statistical variations of the material. So this adjustment of the sigma E is the result of six fractional factors. Each of these six factors is calculated from known data which describe the influence of a specific condition on fatigue life. Those factors are, the first one is the surface condition. We denote that as Ka, such as polish, ground, machine, asphalt, corroded, and etc. Surface is perhaps the most important influence on fatigue life. Size, Kb. This factor accounts for changes of which occur when the actual size of the part or the cross section differs from that of the test specimen. Third, load, denotion of that as Kc. This factor accounts for differences in loading, for example, bending, axial, torsional, torsional between the actual part and the test specimen. Fourth, the temperature, Kd. This factor accounts for reduction in fatigue life, which occur when the operating temperature of the part differs from room temperature. Or we say that as the testing temperature. Fifth, reliability, Ke. The factor accounts for the scatter of test data. So we can get the same a large number or large sample of data. From that, we can plot and then check the reliability of that structure. For example, an 8% standard deviation in the test data requires a Ke value of 0.868 for 55% reliability and 0.753 for 99.9% reliability. Miscellaneous Kf. This factor accounts for reductions from all other effects, including residual stresses, corrosion, plating, metal spraying, fretting, and others. These six fractional factors are applied to the laboratory value of the material endurance limit to determine the allowable cyclic stress for an actual part. So, design consideration. You have to avoid several type of factors that going to induce the high fatigue failure. For example, fretting, and then avoid stress concentrations, and also the corrosive environment. So what we need to do is have to have the good surface finish, cover the surface, okay, short pinning, and then appropriate heat treatment. The last one, choose material that is more resistant to fatigue, which is high strength material. Okay, for the fracture mechanics considerations, fatigue testing under strain control condition is implemented to predict the effects of stress concentration on the fatigue behavior of structure. So sigma strain control means we fix the deformation while we varies in terms of the load. So if you see here, the strain controls test specimen as in this case, and then we put this on the top of free body of the structure. From that, the structure under stress control the condition. Okay. Okay, for the mean stress effects, we have several types of load in terms of the SN curve. But of course, we have different type of material or different type of structure. So this is how we determine the SN curve for each type of material. So sigma A, sigma M can be obtained once you have the SN curve. This is the constant life diagram where based on this value sigma A, we can plot for the same material, and then it reach the sigma U as the ultimate stress, where it can cross the x-axis, where the x-axis we plot that the sigma M that we obtained from the previous graph. So the mean stress effects, the empirical curves to estimate mean stress effects of fatigue life, we have several types of person that contribute to develop this mean stress effects. For example, the Soderberg 1930. So this is his theory. Sigma A divided by sigma E prime plus sigma M divided by sigma Y equal to 1. So the same goes to the Goodman 1899. He derived this equation. Gerber 1874 this equation, and Morrow 1960 this equation. So sigma Y here refers to the yield stress, means it is depends on the type of material that you apply to the structure. Sigma U the same, the ultimate stress. Sigma F the true fracture stress, and sigma E prime is the effective alternating stress at failure for a lifetime of NF cycles. So, based on this theory, they plot a graph that to resemble all of this relationship. For example, if you see the plot A here is actually refers to Soderberg, while B is referred to Goodman, C Gerber, and D for Morrow. So for the general observations, most actual test data tends to fall between the Goodman and Gerber curves. Second, for most fatigue situations, R less than 1, in which small mean stress in relation to alternating stress, there is a little difference in the theories. Third, in the range where the theories show large differences, in which R values approaching 1, there is a little experimental data. In this case, the yield stress may set the design limits. Fourth, the Soderberg line is very conservative and seldom used. Use of empirical curves for an infinite life design. Use a particular curve such as the Goodman, where he mentioned that sigma E prime is actually equal to sigma E, the endurance limit, where sigma F is infinite. So any combination of mean and alternating stresses that are to the left of the curve are deemed safe. Those in the right are not. Okay, he plot this curve, and then this is mentioned that to the left curve is, which is below or inside this curve, is in the safe region, while if you get the value outside of the plot, it will be unsafe region. So this is the plot of infinite life curve. How they plot this? The sigma E is at the y-axis, while sigma U at the x-axis. So they get the value of the plot by matching this line. Okay, use of empirical curves and SN data for an finite life design. A given combination of mean and alternating stresses is taken to lie on a constant life curve such as the Goodman line. So this is the Goodman line just now. The curve is then used to solve for the effective purely alternating stress sigma E prime that will cause failure at this same lifetime. So they want to find what is sigma E prime. So we need to apply what is the value of sigma A. For example, they take this point. So sigma A you can obtain based on this number. Sigma M from this number. And then sigma U is what? Value of being plotted here. So from that you can get what is sigma E. So using the effective alternating stress, determine the lifetime for the stress and the corresponding original alternating and mean stresses from the SN diagram for the given material. So basically, we can take the same value if you have here, what is your NF, what is your sigma E prime, and then what is your cycles to failure. From this, we can plot this curve using Goodman equation. Okay, starting from here, and then you can get this curve. That's why they give you in terms of this line. So you can test or check this, the same procedure, how to change from this alternating stress to the Goodman curve or constant life of NF cycles plot here. Okay, without that, next topic will be the fatigue design method, where we're going to cover in the next lecture. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.